Welcome everyone to San Luis, the 105th meeting of the AAVSO. It's wonderful to welcome you here, and I'm really looking forward to our discussions, our research, our interactions, everything. So our first speaker is a keynote speaker tonight, and we are very privileged to hear from Professor Horace Smith. I met Professor Smith for the first time at CTIO down in Chile. And we had this absolutely fascinating discussion on our LiDAR stars, pulsating stars. And up until that point, I don't think I knew as much as I know now. But so that was my introduction of pulsating stars. He's no, absolute pleasure. I learned so much, and that was actually my, as I said, my introduction to pulsating stars. Professor Smith is a professor emeritus from Michigan State University, and tonight he's going to talk about learning from pulsating stars, progress over the last century. So with that.
Thank you, Stella. Well, I was pleased to agree when Mike Simonson asked me to give this talk. But it became pretty clear from the beginning that there was much more that could be talked about on variable stars than we could possibly cover this time in this space. And this shows why. This is a HR diagram. If I get over here, I'll be out of people's way a little bit more. HR diagram, and each of these little spots that people in the back probably can't read at all are different kinds of pulsating star that are now recognized. We have the classical instability strip from the Cepheids, the Aurora stars, the Delta Scuti and SX Phoenicis variables. We have the long period Myra variables. We have a, it's a variable screen. The cooling strip for white dwarfs, white dwarf variables. We have main sequence variables, all kinds of variable stars. So rather than review everything, I thought I would talk a little bit about some of the lessons, some of the major stories of variable star astronomy since they were realized to be variables, and talk a little bit about some things that AAVSO members can do, particularly with the Aurora stars, Cepheids, Delta Scuti stars that I'm most familiar with. And that means I'll be neglecting a number of variables, but we have a lot of talks during the meeting, a lot of talks that will cover many of those other stars. So, let's talk about discoveries. Now, first pulsating variable found, Myra, 1596. But of course, it's centuries before it's realized it's a pulsating star. And you may be wondering about why I have a picture of a rather dyspeptic-looking goose on this slide. That's because the story goes that Fabricius, who found Myra, first noticed it was doing something variable, was a pastor. And the story goes that he was murdered after accusing someone of being a goose thief from the pulpit. So there are all kinds of, being a variable star astronomer does not get you out of trouble in the rest of your life. Something we'll see a number of times during this talk. For Cepheids, a few more centuries have elapsed. The observing British team of Piggott and Goodricke. Goodricke we have a picture of. Piggott we apparently have no contemporary portrait showing him. So young, deaf astronomer at the time, but makes a number of naked eye variable star discoveries along with the Piggott, and then gets selected at the young age of 21 to the Royal Society dies of pneumonia or similar disease just before he can hear about it. So no goose involved in this episode as far as I know, but observers have a difficult time. How about Aurora stars, star dear to my heart? Periods of about half a day, giant pulsators, typically 4 to 6 times the diameter of our own sun. And their story goes back a little more than a century. And with 2 Harvard College Observatory astronomers, one working with globular clusters, Solon Bailey, you see in the lower portrait, and the actual discoverer of the prototype star, Aurora itself, however, is Wilhelmina Fleming, who you see in the upper portrait. And she discovered Aurora itself sometime on photographic plates before about 1901, when its discovery was announced. So we've had those known Cepheids somewhat more than 2 centuries, Aurora stars somewhat more than 1 century, the Miras now more than 4 centuries. Up to this time, though, early 1900s, it is still not accepted that any of these stars are pulsating variables. They don't know what for sure is causing these light variations. Some people speculate that one side of the star is bright, one dim. Some people think that stars like Cepheids are some kind of binary star, because it's already known that the radial velocity changes over the cycle. And they were thinking this was radial velocity due to some kind of odd orbital motion rather than due to pulsation, the atmosphere going in and out. The first main sequence variable star was found before it was known there was a main sequence. This is 1902, and by Edwin Brant Frost up at Yerkes Observatory. And this was also, I think, they found the Beta Cephei to be a variable. And I think this was also the first class of variable stars to be discovered spectroscopically before its photometric variability was found. These are upper main sequence pulsators. The amplitude is usually low in the photometric variation, at least for the time. But the radial velocity variation was detected before the photometric variation. Well, here we have another kind of variable star found, and by someone who's been a longtime friend of the AAVSO. And as I was talking to him earlier, any talk that has a picture of Alo, and it can't be all bad. And he was just telling me in 1964, he was looking at doing photoelectric photometry of a white dwarf star, not with the intention, not with the idea ahead of time that it was a variable, but that he realized that few of those stars had good photoelectric photometry at the time. And it was only during the observing in 1964 he noticed variations, eventually realized that this was a new discovery, not some mistake in the photometry. And this led to the whole series of works on white dwarf pulsators. Now, these are very short pulsators. The time scale can be minutes, or tens of minutes. So these are stars that are very different from the kinds that we've looked at so far. And then we have the whole range of solar type astroseismology, helioseismology variations that perhaps we can consider as having begun with the discovery of the 5-minute oscillations in the sun, which we now know are due to many, many different non-radial modes all being excited. And Leighton in the 1960s was one of the pioneers in this whole realm. So we have a wide range of different kinds of pulsating star, And let's go back to look at some in a little bit more detail. Let's start with the Cepheids. Now, this is a good result from a good Midwestern astronomer. Joel Stebbins started, I think, did observations in Illinois, later in Wisconsin, also in California, it must be admitted later on still. And this is his pioneering photoelectric light curve of Delta Cephei, 5-day pulsating Cepheid. The scale goes up toward magnitude toward the top, but it's really brighter at the top. It's just the definition of the difference in magnitude that he's using here. So 1908, this gets published. It's still before it's realized that Cepheids are pulsating stars. The biggest theory is still that there's some kind of odd binary. But clearly the light curve is not like that of any ordinary binary star. It's nothing like an algol variable, a W Ursa Majoris variable. So people were having a hard time already with this particular idea. So Cepheids begin to become particularly important, not only because there were some bright ones that Stebbins begins to look at, but also because of a series of observations begun by the Harvard College Observatory. Some of you may recognize Edward Charles Pickering in this image. He became director of the Harvard Observatory in the latter part of the 1800s and was a demon for collecting observations. He started observing all kinds of things, but he said stellar photometry, stellar spectroscopy are going to be major goals of my observatory, and variable stars as well. And with the desire to obtain photographic observations at the time of the entire sky, he begins setting up a Harvard observing station in the southern hemisphere to complement observations taken from near Cambridge. And that's a picture of the Harvard observing station at Arequipa, Peru, set up in the later 1800s. Not a large telescope by modern standards, but it's getting some of the first intensive observations of photographic observations of things like the Magellanic Clouds. And it's with the Magellanic Clouds that the story becomes particularly interesting as regards Cepheids. The two clouds, both visible from Arequipa very well, although there were complaints that best season for Magellanic Clouds was often a rainy season at the Arequipa Observatory. But still, a lot of photographic plates begin to be accumulated at the Harvard Southern Station and sent back north for analysis, back to Cambridge. And it was there in the early 1900s at Cambridge that Henrietta Leavitt takes up the task of actually obtaining photometry of some of these variable stars. First, she looks at the plates and discovers there are a lot of variable stars in the Magellanic Clouds. And at first, however, there are not periods for most of these. She finds something like 1,700 variables in the large Magellanic Cloud. But getting enough data to get periods for them is quite a struggle, particularly when you realize this is before days of even hand calculators. Some of these people work with logarithm tables and doing period searches. This is not an easy task. But in 1908, she has enough data to suggest that the brighter and also Cepheids were in the small Magellanic Cloud were also the ones with the longest pulsation period. In 1912, a paper is published. She publishes a paper in the Harvard Circulars with results from 25 stars that look like Cepheids from their light curves in the small Magellanic Cloud. And this is her first paper her first diagram of the period luminosity relation. Now, it looks like there's a relation for two different types of Cepheids here, but she's really plotting the peak brightness of the Cepheid and the faintest brightness rather than the mean brightness. And that's why you get two curves going up here. These are really the same 25 stars. The type 2 Cepheids are still in the future. No one's thought about those yet. But this is a big discovery. It's kind of neglected, unfortunately, at Harvard itself. If you look at the Harvard records, they don't really make use of this idea of the period luminosity relation at Harvard itself until after the death of Pickering, the director. And he didn't pick up on the importance of this perhaps as quickly as some of the other people working on variable stars outside of Harvard at the time. This is the period luminosity relation for Cepheids, of course, is going to become the key to using Cepheid variable stars as distance indicators. And that period luminosity relation for Cepheids is now often called Leavitt's law, after Henrietta Leavitt. And here are two versions for type 1 classical Cepheids, a recent one in the visual and one in the infrared. The infrared is not perhaps so good for discovering Cepheids because the pulsation amplitude is very small in the infrared. But if you just want the distance, and you already know it's a Cepheid, the effect of interstellar dust and perhaps the effect of things like metallicity are much smaller in the infrared. So the infrared is a very good tool now. Of course, that was long dreams. Infrared astronomy were dreams at the time of Henrietta Leavitt's work. It's just photographic photometry at the time. Okay. Note, this is even 1912 when Henrietta Leavitt publishes her paper on the period luminosity relation. This is before it is generally accepted that these are pulsating stars. The use by people outside of Harvard, of course, Hollow Shapley would later, after the death of Pickering, become the director of the Harvard College Observatory. But at this time, 1914, he's just finished his PhD degree at Princeton on eclipsing variables and is just moving out to Mount Wilson. And there he carries out in the late teens a series of observations on globular clusters. Then make use to get the distance scale to globular clusters. He uses his own calibration of the Leavitt's law. Now, there wasn't a direct calibration at the beginning because no one knew how far away the Small Magellanic Cloud was. So Leavitt's original period luminosity relation was in observed apparent magnitude, not absolute magnitude. Shapley tries to turn that, and does, after a fashion, into a calibrated absolute magnitude scale. We know it wasn't perfectly right. We know there were errors in his early calibration, but nonetheless, it was good enough to show that the globular clusters were far from us, and that the center of the system of globular clusters was far from the location of the sun, leading Shapley to the idea that the sun was not at the center of the Milky Way galaxy, unlike what many others thought at that time. And in the 1920s, also at Mount Wilson, Edwin Hubble finds a variable star in this case, in this picture, in Andromeda, that he realizes is not a nova. So crosses a variable gets written in. He realizes that its light curve is varying like a Cepheid. You can use the period luminosity relation to get its distance. And you can establish that things like Andromeda and other neighboring systems are external galaxies, that the Milky Way is not the only big galaxy. Now, has anyone played with Google Ngrams? Has anyone heard of those before? There's a little Google tool you can go to, and it looks through a whole bunch of written material that Google has scanned and looks for the frequency at which different words are used. So I thought in this connection it might be interesting to do a little Google search on the word Cepheid and see what happens with it. So this is what we get. The higher the peak, the more often the word Cepheid is found compared to other words in the publications of the time. And that's year at the bottom. If you can't read that, that's going up to the year 2000. Oh, where it begins to jump up is the year 1900. So nothing much throughout the 19th century. The whole idea of Cepheids as a particular class of variable star, the whole idea of their usefulness in astronomy really comes with the work of Leavitt, Shapley, Hubble in the early 20th century. And wow, and around the 1920s, it looks like Cepheids are really popular. They get to be used more often than now. I don't know if there's a periodicity in the trend there of the Cepheid variation. I didn't try running it through any of the period finding routines here, but someone could give that a try. Yeah, it's got a decay, obvious decay, but hopefully the mention of Cepheids won't go to 0 in the future. There is the Leavitt and the Hubble time periods here. You can try it. You can put in your favorite variable star and see when it began to be talked about, when it was popular. So I said up to 1912, when Leavitt's paper is published, people are thinking of Cepheids. Maybe they don't know for sure why they're varying in brightness. And a lot of people still think there's some kind of weird binary system, even if they're not eclipsing binaries. Some people had already put forward the idea of stellar pulsation, but it had been rather neglected up to this time. I think the paper that really changes the picture is one published in 1914 by Hollow Shapley, who argues that Cepheids and RLR stars are not changing in brightness because they're binaries, but that they are pulsating. And he advances a number of arguments in this paper, but the one that seems critical to me is this is just the time when the division between giant and dwarf stars has come into astronomical usage, just before this time. And Shapley was a student of Russell at Princeton, who, of course, in the Hertzsprung-Russell diagram, one of the discoverers of the idea of giant and dwarf stars. And he says, you know, looking at what we know about these Cepheid stars, they are giant stars. They are not dwarf stars. But if you look at these orbits that people have calculated under the assumption that Cepheids are orbiting stars, the orbits are so small that they'd be inside the body of a giant star. That didn't seem likely to Shapley. So he said, these have to be changing in brightness for some other reason. Cepheids may be pulsating stars. Now, Shapley was not really a theorist, but Arthur Stanley Eddington certainly was. And he took up the idea of pulsation theory in the years after Shapley's work, advanced it to a great degree, and put it on a much firmer basis, even though decades more would still elapse before the actual mechanism for driving the pulsations within Cepheids would be discovered. But even before knowing that, he was able to put theory to use. He said, suppose we're thinking about how stars might be powered. This is 1920, just before 1920. We don't have theories of nuclear reactions worked out yet. The idea that energy could be contained within atoms is a new idea at this time. And one of the older ideas was that gravitational contraction of stars could keep them shining. The star would be slowly shrinking. It would give up some of its gravitational energy, would be radiated away as energy. This could power a star. So as soon as he gets to thinking about stellar pulsation, Eddington says, what can we say from stellar pulsation about the energy sources of stars? He said, if a star is contracting by the basic pulsation equation that we'll see shortly, the period times the square root of the density equals a constant. If the star is contracting, the period should be decreasing. And he knows how fast it should be contracting in order to keep a Cepheid shining as brightly as it's observed. He says, well, I don't know a lot about Cepheids, but what we do know about them from how big they seem to be, it looks like in order to power a Cepheid, like Delta Cephei, that star should be decreasing in period by something like 40 seconds a year. This period should be going down pretty fast. And, well, Pigott and Goodricke, they were started observing more than 100 years ago, even at the time that Eddington was working. So he and Hertzsprung look at all the period change data of Delta Cephei obtained since that time. And this is a modern version of the O-C diagram for Delta Cephei. So the observed minus the calculated time of maximum light from, assuming a constant period, plotted against, in this time, epoch number of cycles, taken from a recent paper by Engel et al. And it does, in fact, turn over. It's not a straight line, and that means a period is changing. In this case, the change in period is a decrease, but the rate of decrease is not that much different from what Eddington and Hertzsprung found, about minus a tenth of a second per year, nothing like 40 seconds. So a century ago almost, Eddington is able to discredit the idea that Cepheids could be powered by gravitational contraction by making use of the idea that they were pulsating stars. So pulsation is a tool, not only in pulsating stars are not only used to say distance by Leavitt's law, but they're a tool for studying the energy sources and the internal structure of stars. Now there's the basic pulsation equation, actually found before Eddington's time. The period times up, looks like on the Greek letters didn't come out here. That X is usually the Greek rho for density, but equals the pulsation constant Q. So for the low density giant stars, big red giants like Mira's, we come up with periods of hundreds of days. The Q does vary a little bit with the nature of the star, but the density is the main change. For white dwarf stars, very high density, periods are down around a minute. Now, I'm not going to say much about pulsating modes, but there are different ways that stars can pulsate. And they can either pulsate radially, in and out, or non-radially. In the radial case, the longest period of the star is called the fundamental mode. And generally, such a star just has one non-pulsating point node down the center, pulsates in the outer part, in and out. First overtone pulsators generally have a node in the center, radial pulsators, and then a surface outside that's also a node from which things go in and out. And you can go on to higher and higher overtones. We won't talk about that too much, and certainly not the theory of them, but we will look at some light curves of multimode stars later on. Here is a modern version of Leavitt's relations, period luminosity relations for Cepheids in the Large Magellanic Cloud. Now, you see, we now know there are two types of Cepheids, the classical Cepheids and the type 2 Cepheids, the W Virginis stars. But you notice here that the classical Cepheids divide in two. There are two lines at the top for the classical Cepheids. That's because we have the fundamental pulsators and first overtone mode pulsators plotted on this diagram. And the first overtone ones are shifted to shorter periods at the same luminosity. So these different pulsation modes are easily picked out in things like period luminosity relation if you're looking at something far away, if it's a big radial mode at any rate. And here are the Olga light curves. Nice big Cepheid looking light curves for the fundamental mode pulsators. First overtones are in the middle. Not quite so asymmetric usually, but not really symmetric. And on the second overtone, looking almost sinusoidal on the side. And these stars, the brightest ones are toward the top in this plot. The fainter ones are toward the bottom. These are all large Magellanic Cloud Cepheids. Now, I'm not going to get into the non-radial modes much at all. They're so complicated, it's hard to keep in your head with the L and M oscillations. But they do make for pretty pictures. These are theoretical pictures. You can imagine the red parts moving one direction, the blue moving in the other direction. There are all kinds of different modes that are possible in the non-radial case. So let's leave it for a pretty picture. Except another pretty picture just showing the many, many non-radial modes excited in the sun. And here you can see it's frequency versus an indicator of mode type along the bottom. Many, many modes excited. Let's talk a little bit more about one more use of Cepheid variables before we talk about things that AAVSO observers can do. You can use different kinds of pulsating variable stars as indicators of stellar populations. They're found, different kinds of Cepheids are found associated with particular ages, sometimes particular metal abundances. And when you identify those objects in another system, that tells you that kind of population exists. One of the pioneers in using variable stars in this way was Cecilia Payne-Kapowski, another Harvard astronomer, but it was many years after the time of Pickering in the Shapley era and later. And if you see a type 1 Cepheid, that's generally a young population, a young stellar population. If you see an Aura Lyrae star, half-day period, pulsation, that tells you that an old population is present. Those are found in globular clusters. Those are stars about 10 billion years or more old. Here's one of Payne-Kapowski's diagrams from a 1974 paper, The Large Magellanic Cloud, which is looking at the distribution of Cepheids of different period, classical Cepheids of different period. The idea that their ages are a little bit different. In the scale she had there, 3 to 4 day period Cepheids would be 150 million years old, typically. Evolved stars. The 6 to 8 day Cepheids, longer period, brighter. They're a little about half the age. I think you can kind of see here there's a suggestion that the pattern of births at this age is a little bit different. Modern versions using the surveys of variable stars of Cepheids and Magellanic Cloud can do things like make three-dimensional maps. Now the color doesn't come out too well here, but if you look at this paper, each Cepheid is color-coded by its distance in this diagram. And you see kind of the same basic pattern of the bar and the outlying areas of star formation that we saw in Payne-Kapowski's diagram. But now we see it with the 3D. You have the least the authors claim the distances are good enough that we have a good 3D picture of the distribution of Cepheids. So let us return to our HR diagram. We'll hear more about Myra variables, long period variables, and Leanne Wilson's talk tomorrow morning. I think you're going to tell us, David, about supergiant semi-regular variables. Is that right? I borrowed the diagram from someone else. Well, you can, yeah, they're, oh, yeah. Imagine them up at the top end. They're kind of figurative. But I want to talk about some of the variables in the classical instability strip and some of the things that AAVSO observers have done and can do to investigate them. So these are the Cepheids. So you go from periods the longest near 100 days down to a day. Aurora stars, typical periods near half a day. Delta Scudi or Essex Phoenicis stars, typical period near a tenth of a day. And these are the stars I'm going to be mostly talking about for the little bit remaining in the talk. And there are three areas of investigation that I'm going to suggest are interesting. Period changes, modal stability of multimode pulsators, and the Blazhko effect, which is a long period variation superposed upon the half-day variation of Cepheid RLI variable stars. So Eddington in 1918, remember way back when we talked about delta Cephei, Eddington had already pointed out the importance of period changes, and now we have much more sophisticated models of the evolution of stars. And we can use period changes in principle, if we have long enough data, to test whether the observed period changes match now the nuclear burning theories of the evolution of these stars, rather than just the gravitational contraction idea that Eddington was able to test back in 1918. And period changes are a good job for people like to observe for a long time, right, Jerry? If you like to have years, decades, centuries of data before you come to a conclusion, period changes are for you. And do the observed period changes match stellar evolution? If so, or if not, what kind of period changes are observed? And what kind are there particular odd period changes associated with particular kinds of stars? Of course, the O minus C diagram is still a very important tool when looking at this, the observed minus calculated time of maximum light, usually. If you get a nice turnover like the top one, it's a decrease in period. A turn up like the bottom O minus C diagram, the black one, is an increase in period. And if the period rate is changing slowly over time at a constant rate, and the period change rate is small compared to the period, your O minus C diagram should look rather like a parabola. And you may remember this diagram if you were at the meeting last year. I showed it of a Cepheid in the globular cluster M13. Not too bad a fit to a parabola, but maybe not perfect. So this would be consistent with actually not too bad for the predicted rate of period change due to nuclear burning, the evolution, smooth evolution through the HR diagram of a type 2 Cepheid in the globular cluster M13. So not a chalk one up maybe for stellar evolution theory. Now let's look at an RLRA star. This is a diagram from Jerry of a XC Cygni. long a favorite of AAVSO observers, period a little bit less than half a day, and there is the observed O minus C diagram. You can't see, I don't know if you can see the labels too well, but it's not a parabola. Here's another diagram Jerry sent me. AR Hercules, another R Lyrae star, not a parabola. There are some R Lyrae stars that look more like they obey the parabolic form you expect from star evolution, but clearly there's some kind of period change noise from some other phenomenon in the star that is affecting the O minus C diagram. There are some ideas as to what this might be, but they're not very well pinned down. I should say that XC Sig and AR Her are also two stars known to show the Blaschko effect that we'll talk about in a little bit. And that such stars may be more likely to have these irregular O minus C diagrams. Multimode pulsators. Some of them, like this Exis Phoenicis star, go through several appearance cycles during the course of a single night. But you can see the cycles don't repeat perfectly. And if you do an analysis, you find there's more than one mode excited at the same time. And this is an interesting idea. What are the modes that are excited? And do these modes, do these periods of these modes, the relative amplitudes of the different modes, stay stable over time? So here, if you were looking at a multi-mode variable, you could try to establish its multi-mode. See if the amplitudes of different modes are constant if you come back and look at the star later on. Do the variables switch between single mode and double mode behavior? Do the periods of the different modes change? And if so, how? Here's a paper from the Ogle survey showing that you can apparently switch between double and single mode observations. Over on the left, the light curve with all the scatter is plotted with a single period, but it really has two modes oscillating, and that's why you see all the scatter. But they come back and look at it a little bit later on. You get the nice smooth light curve, one dominant mode. The amplitude of that mode is a lot bigger than when it was a double mode. Things can change. And exactly why this happens and how it happens is not very well known. The Blaschko effect, the final topic. This is from a diagram Doug Welch made from Macho data. The Blaschko effect was first found in R Lyrae stars. There are some similar phenomena now seen in other pulsators. The main period is about half a day, remember, but over a span of tens of days, the shape of the main cycle changes. And this can lead to variations in the O minus C diagram on that longer scale as well as the amplitude. This has been known since Sergei Blaschko called attention to it more than a century ago. His explanation is still fought over. It may have something to do with mode period doubling now discovered actually with Kepler observations of R Lyrae itself, where alternating peaks vary in brightness. This was not found from the ground because if you're observing from a single location, you see every other period of R Lyrae. You miss the one in between, you don't see the period doubling. But it's also not there all the time. And some people have suggested that the period doubling may be indicating another mode that may have an effect on the Blaschko effect. That's uncertain, however, still. So Blaschko effect projects show that a particular star does have the Blaschko effect. If it does the amplitude and period of the Blaschko effect stay constant all the time? Do non-Blaschko stars turn into Blaschko stars, or vice versa? RLI itself was found by Hollow Shapley at what we now know as the Blasio effect in more than a century ago, just about a century ago, I guess. In recent years, the amplitude of the Blasio effect that has made that little O minus C diagram of scatter has been going down, as if the Blasio effect were going away. Now, that's happened before, though. So it doesn't necessarily, because it's going away now, it doesn't mean it's going to disappear and never return. But it means the phenomenon that once was thought this coming and going of the Blasio effect was periodic. Now that doesn't seem to be the case, and why it happens is still mysterious. But these are all observations, and why do I suggest that all problems that AAVSO observers can tackle? Partly because AAVSO observers can get data for a long period of time. And for a number of those projects, like the period changes, you need data not for a season, but for years, decades, centuries if you last that long. An organization can last that long. And other AAVSO observers are located all around the world. So if you're doing some kind of campaign where you're trying to worry about phenomena that might not be observed with a daily observations on a nightly schedule, AAVSO observers can help. So by showing those pictures earlier in the talk, I wanted to remind people that variable star astronomy is done by people, not by photometric photometers or CCDs or computers. And this diagram made by the AAVSO, I think actually made it some years ago, shows the distribution of AAVSO observers. And what we need is a lot more people working on all these projects, getting the observations to solve some of the questions mentioned. And these points and many other points, and I hope help to that end. So I'll end on that diagram. Thank you.